Hi everyone, and welcome to our lesson today on resonance. Resonance is a huge foundational concept for organic chemistry. So hopefully our lesson today will give us a good idea of what resonance is, some electron shift patterns to know, and some important key terms to keep in mind when thinking about resonance structures. Alright, so we're going to first start by talking about what resonance is. So resonance is when multiple Lewis structures can represent the same molecule. So if you consider something like nitrate, for example, there's 3 different Lewis structures that you can use to draw and represent the same molecule. And if you remember from Gen Chem, we learned about Lewis structures. So this is really where it can play a big role in organic chemistry as well. So the actual structure of nitrate is an intermediate between all of these different drawings of it. And so when we're looking at a representation of resonance for a molecule like nitrate, something good to know is that these arrows, which represent resonance arrows, are not the same thing as equilibrium, which looks a little bit more like this. So it's important to not mix these concepts up because equilibrium's experimentally not the same as resonance. And also in resonance, we have electrons that hang out in these overlapping p orbitals here. So if you can imagine, these electrons are hanging out in these pi electron clouds. There's a lot of space for them to roam around in. And this delocalization of electrons basically leads to increased molecular stability. So if you remember, electrons really like to repel each other since they have the same charge, and they want to get away from each other as far as possible, if possible. And so when you have a lot of volume and space for these electrons to delocalize and roam around in, it makes a very stable molecule. And resonance also leads to planarity, which means that these atoms are all in the same plane. And part of this is due to how these electrons are really delocalized, allowing for a very flat molecule to form. So resonance basically leads to planarity, molecular stability, and it has a lot to do with the electrons roaming and kind of shifting around in the molecule. So there's 4 major electron shift patterns that we should keep in mind when considering resonance. The first is a lone pair and pi bond switch. And so let's look again at nitrate here. And before I go further, I want to basically highlight some important terms to know. So each of these individual drawings of nitrate are considered resonance contributors. So they're all in some way contribute to what the actual structure of nitrate looks like. So that's kind of why we draw all of these out here. So again, the first switch that we should keep in mind is a lone pair and pi bond switch. So obviously it's going to include a lone pair and pi bond. So let's look at this contributor and figure out what's kind of different between them. We see that there's this double bond here, and then there's a double bond over here instead. So this means that this lone pair over here on this oxygen goes to form this pi bond here. And make sure you understand what the curved arrows mean. These electrons start here, then they go over here. It's kind of intuitive, it makes sense. So these lone pair electrons go here to form a pi bond, but since nitrogen can't have 5 things attached to it, this double bond here needs to actually, these pi electrons need to go back and form a lone pair over here. So that's how you go from this structure to this structure. And going from this structure to this contributor, you want to see how these double bonds kind of switch places here. So we're going to move this lone pair to form this double bond, and this pi bond over here, these electrons are going to go and form a lone pair on the oxygen again. So that's how you get these 3 contributors for nitrate. The next type is a pi bond and open valence shell switch. So again, we have a movement of a pi bond going over here, so then you have this formation of a new double bond over here. But as a result, this open valence shell, although it gets filled over here, is now over here on this carbon now, which was on the other side of that pi bond, if you recall. So if we were to draw the next structure, or the next contributor, representing this change over here, we would have this molecule. And I encourage you to maybe try it yourself as well. So we're going to have this double bond over here still. This is the basic structure of the molecule. So we have this pi bond shifting over here, so we're going to have this over here. And no longer is this open valence shell in existence, so there's no plus charge that's going to be here on this carbon. And similarly, we're going to still have this double bond over here, which I'm going to add in right now. And then, as a result of these pi electrons moving over here, we're going to have now an open valence shell on this carbon right here. So I'm going to add in a plus sign right there. So that would be the next resonance contributor that we would draw over here. The third type of shift is a lone pair and open valence shell switch with a bond. So that's kind of a mouthful. But here we have formaldehyde, and this basically involves moving a pi electron some lone pair electron somewhere to form a pi bond. So in this case, we have this oxygen with some lone pairs. We're going to move that over here. There's a pi bond that forms right here, and as a result, now that carbon has 4 covalent bonds as opposed to only 3 covalent bonds here and a plus charge, it has a full shell. So this shows how the electrons can move, they form a pi bond, and now there's no longer an open valence shell. Or in some cases, if you have like a nitrogen or something, you might have still a plus formal charge that remains. And the most important thing to keep in mind here is basically that there's some pi bonds forming as a result of lone pair electrons moving over. The fourth type of switch is a pi bond switch, and this is benzene. It's very common to represent pi bond switches with benzene. So here you see how these pi bonds and double bonds are kind of switched around in terms of locations. So we look here and we can see how these pi electrons kind of moved around, forming this structure over here. So that one's pretty easy to tell. So what's the point of drawing all of these resonance contributors? It's really just basically for us to understand what the actual structure looks like and to get an idea of what the resonance hybrid is. And that's basically an average or blend of all the resonance contributors that we've drawn. And it's also the most accurate representation of what the molecule really looks like. So the way to draw a resonance hybrid, and that's important to know, is how to draw one. You basically want to draw first the resonance contributors. So this is ozone. You're going to draw the resonance contributors that you know of, and you're going to draw a Lewis structure that encompasses all the things that are the same in each of the contributors. And then from there, we're going to add in the, I'm going to close out of that. We're going to add in the partial pi bonds and the partial charges. And I'll show you guys how to do that as well. So let's take a look at ozone over here. These are the two resonance contributors for it. And so the first step to drawing a resonance hybrid is identifying the features that are the same in all of them. So ozone has, these 3 oxygens over here. It also has these sigma bonds that we're going to include so that these oxygens can, bond together. Then if you look on this structure and this structure, the middle oxygen has a positive formal charge. So we're going to include that here because that's on both of them. And if you look at these oxygens on the side, there's a negative charge on this one and then a negative charge on this one. So the negative charge can basically go on either of the oxygens. So we're going to represent that with a delta minus, which are partial charges. And this basically means that occasionally the electrons will be more heavily delocalized onto these oxygens here. If you imagine it, they're kind of pulling these electrons towards themselves. And then to represent the partial pi bonds, you see how there's a double bond here and a double bond here, so it can go in either location. So we're going to represent that with dashed lines. And if you want, you can add in the lone pair electrons here. So if you imagine these are lone pair electrons, sorry, these are really questionable drawings. So you can add in the lone pairs if you'd like to kind of represent that. So that would be this and this, this and this. All right, so that's kind of what the resonance hybrid would turn out to be for ozone. So another thing that's really good to know is how to determine which contributor contributes the most to the resonance hybrid, which one has, the one that has the greatest weight. And so some important things to consider, this is a really brief summary of it, but you want to consider which one has the fewest avoidable open valence shells. So you don't want something with like, for example, you would prefer something that doesn't have, an open valence shell on the carbon, for example, because that's just kind of not as stable. That brings me to my next point. You definitely want something with a lot of stability. You want something with the greatest number of covalent bonds. So maybe having something like this as opposed to something like this, which only has 3 covalent bonds attached to the carbon for whatever reason, as opposed to 4. You also want resonance between the same row elements. So something like this is pretty good because carbon and nitrogen are in the same row. And you also want the fewest avoidable formal charges. So I'm going to put an FC here to represent formal charges. And if you do have to have formal charges, you want the negative formal charge on a highly electronegative atom and a positive formal charge on the less electronegative atom. And the reason for this is if you imagine something like oxygen might be better able to accommodate a negative formal charge since it's pretty electronegative, as opposed to something like carbon, which might not be able to handle these negative charges as much. And so you wouldn't want a negative formal charge on this one necessarily if you had to pick one. So let's look at this problem here. It says in each set of contributors, we're going to choose the major contributor, or the one that basically is the most stable, that contributes the most to the resonance hybrid. So let's look again at formaldehyde here. We have in this contributor a positive formal charge on the carbon, negative formal charge on the oxygen, and then here we have no formal charges. And similarly, we have 3 covalent bonds on carbon here, as well as opposed to 4 over here. And finally, this one has a full octet, whereas this carbon does not. So if we had to pick the one that would be the most contributing, we would definitely want to go with this one for most of the reasons stated above. Let's look at this one now. We have a positive charge on the fluorine over here, and then a positive charge on the chlorine over here. And it looks like the covalent bonds are maximized in both contributors with 4 bonds. So if we wanted to pick the one that had the most or the one that was the major contributor, you'd want the positive charge to be on the less electronegative atom. And fluorine's electronegativity is about a 4, and chlorine is about a 3.1. So we would probably go with this one because the positive formal charge is on the less electronegative atom. And then let's look at this last molecule here. All of these have the same formal charges. They have the same amount of covalent bonds. The only thing that's really changing between them is where this double bond is located. And it looks like these are all basically kind of the same drawing. So these all equally contribute to the molecule, the resonance hybrid overall. So thank you for listening.